Welcome to G Fun Facts Online. Today, we're diving into a technology that promises to redefine the world as we know it: quantum computing. For decades, classical computers, with their simple language of ones and zeros, have powered our digital age. But some problems are just too complex for them. Imagine trying to map every possible move in a game of chess simultaneously, but on a scale with more possibilities than atoms in the universe. That's where quantum computers come in, and we've just witnessed a monumental leap forward. Physicists at Caltech have built a processor with over 100 quantum bits or qubits, smashing previous records and pushing us from the era of small experiments toward truly large-scale quantum machines. So what does this actually mean? To understand this massive leap, we first need to understand what makes a quantum computer so different. A classical computer uses bits, which are like light switches. They can be either off, a 0, or on, a 1. Simple and definite. Quantum computers use qubits. Thanks to a bizarre but fundamental property of quantum mechanics called superposition, a qubit can be a 0, a 1, or both at the exact same time. Think of it less like a switch and more like a dimmer knob that can exist at any brightness level, including all of them at once. This ability to hold multiple values allows a quantum computer to explore a vast number of possibilities in parallel. The power grows exponentially. Two classical bits can represent one of 4 combinations, like 0, 0, or 10. Two qubits can represent all 4 combinations simultaneously. If you had just 300 qubits, you could, in theory, represent more states than there are atoms in the known universe. But superposition isn't the only trick. There's also entanglement, which Einstein famously called spooky action at a distance. When 2 qubits are entangled, their fates are linked. Measure the state of one, and you instantly know the state of the other, no matter how far apart they are. This profound interconnectedness is a key resource that allows for the incredibly complex calculations needed for advanced quantum algorithms. These properties give quantum computers the potential to solve problems that are currently impossible for even our mightiest supercomputers. We're talking about simulating new molecules for life-saving drugs, creating revolutionary new materials, optimizing global financial systems, and even breaking the encryption that secures our digital world. Now, let's get back to that breakthrough at Caltech. Led by Professor Manuel Endres, a team created a massive array of 100 qubits. Their method is incredibly elegant. They use highly focused laser beams, known as optical tweezers, to trap and hold individual cesium atoms in a precise 2-dimensional grid. Each of these neutral, uncharged atoms acts as a single qubit. This isn't just about the sheer number, though that is staggering. The performance they achieved is what's truly exciting. A crucial metric for any qubit is its coherence time. This is the window of time a qubit can hold its quantum information before the outside world's noise, like tiny temperature changes or stray magnetic fields, causes it to collapse back into a simple 0 or 1, losing all its special quantum data. The Caltech team reported a coherence time of 12.6 seconds. That might not sound like a long time, but in the quantum realm it's an eternity and a record for this type of qubit. Longer coherence means you have more time to perform complex calculations before errors creep in and ruin the result. They also achieved extremely high fidelity in reading the state of their qubits, with a success rate over 99.98%. This is vital, because if you can't accurately read the answer your quantum computer gives you, the whole computation is useless. While they haven't yet entangled all 100 qubits to perform a single massive calculation, they've built the arena, tuned the instruments, and gathered all the players. The next step is to get them all working together in a symphony of quantum computation. Of course, building a useful quantum computer isn't just about packing in more qubits. The journey is filled with enormous challenges. The very sensitivity that makes qubits powerful also makes them incredibly fragile. As you add more qubits, it becomes exponentially harder to shield them from environmental noise and to control them precisely. The biggest challenge is error. Quantum operations, called gates, aren't perfect. Each one has a small chance of failing. In a system with thousands of qubits performing millions of operations, these small errors quickly pile up, rendering the final answer meaningless. To solve this, scientists are developing what's known as quantum error correction. The basic idea is to encode the information of a single, perfect logical qubit across many flawed physical qubits. Think of it like having multiple people proofread a document to catch any mistakes. By constantly checking these physical qubits for errors and correcting them on the fly, you can create a single, robust logical qubit that is far more reliable. One of the leading designs for this is called the surface code, which arranges physical qubits in a 2D grid, just like the Caltech processor. The catch? The overhead is huge. It might take 1,000 or even several thousand physical qubits to create just one stable logical qubit. This is precisely why scaling up the physical qubit count, as Caltech has done, is so fundamentally important. We need these massive numbers to even begin building a truly error-corrected or fault-tolerant quantum computer. The Caltech approach using neutral atoms is incredibly promising, but it's not the only game in town. The race to build a quantum computer is being run on several different technology tracks, each with its own strengths and weaknesses. The most mature technology is likely superconducting qubits, pursued by giants like Google and IBM. These are tiny electrical circuits that, when cooled to temperatures colder than deep space, behave as quantum objects. They're fast and relatively easy to manufacture, but their coherence times are shorter, meaning they're more prone to errors. Then you have trapped ion qubits, championed by companies like Quantinuum. Here, individual atoms are electrically charged and then suspended in a vacuum using electromagnetic fields. These qubits are incredibly stable, with very long coherence times and high-fidelity operations. Their main challenge is scaling up the complex systems of lasers and magnetic fields needed to control them. The neutral atom approach, which we've discussed, sits in a sweet spot. It offers long coherence times and has now proven to be massively scalable. They might be a bit slower than superconducting qubits, but their potential for creating dense reconfigurable arrays is a huge advantage. There are other, more exotic approaches too. Photonic qubits use single particles of light, which are great for communication but difficult to make interact. And then there's the Holy Grail, topological qubits, which Microsoft is working on. These would be inherently protected from noise, but the underlying physics is still highly experimental. The future might not see one winner, but a hybrid approach, using different qubit types for different tasks. So where does this leave us today? We are in what's called the noisy intermediate scale quantum, or NISQ era. Our current processors, with a few dozen to now a few thousand qubits, are still too noisy and error-prone to run the most famous quantum algorithms, like Shor's algorithm, which could break modern encryption. But that doesn't mean they're useless. Researchers are designing special hybrid algorithms that pair these noisy quantum processors with classical computers. They could be used for discovering new drugs and materials by simulating molecular behavior, solving complex optimization problems in logistics and finance, or even enhancing certain types of machine learning. The ultimate goal, however, remains the fault-tolerant quantum computer. The roadmaps from major players like IBM and Google are aggressive, with both aiming to build a useful, error-corrected machine before the end of this decade. IBM, for instance, plans to have a system with over 4,000 qubits by 2025, on its way to what it calls a quantum-centric supercomputer by 2033. The arrival of these machines will have a profound impact. In medicine, simulating molecular interactions could slash the time and cost of developing new drugs. In finance, quantum algorithms could optimize investment portfolios and model risk with unprecedented accuracy. We could design new materials from the atoms up, creating things like room temperature superconductors or catalysts that pull carbon dioxide directly out of the air. But this great power comes with great risk. The most immediate threat is to cybersecurity. A powerful quantum computer could theoretically break the encryption that protects everything from our bank accounts to government secrets. In response, a global effort is underway to develop new, quantum-resistant encryption standards to secure our data for the coming quantum age. The Caltech team's creation of a 100-qubit processor isn't just another incremental step. It is a landmark achievement, a clear signal that the quantum revolution is accelerating. We are moving from theory to practice, from small-scale curiosities to large-scale engineering. The path to a fault-tolerant quantum computer is still long and full of challenges, but it is becoming clearer with each breakthrough. The scaling of this revolution is well underway, and its impact will shape our world for generations to come.